This is video number 100 in our series on tensor calculus. In this video, we're going to finish up the entire series with a very brief introduction to the subject of Riemannian geometry. But before we do that, let's do a very brief review of the topics that we've covered in the series so far. We began in videos 1 through 5 by covering some very basic information about spaces and coordinate systems. In videos 6 to 26, we began the analysis of vectors and tensors and showed how to work with them in the form of tensor equations using the appropriate tensor calculus syntax. Videos 27 to 42 were devoted to an in-depth analysis of the covariant derivative. This new operation proved to be an invaluable tool applicable to almost everything we did going forward. Next, we turned our attention to determinants in videos 43 to 56. This led to the development of several new key objects such as the volume element and the Levi-Civita symbols. In videos 57 to 75, we introduced surfaces, which we analyzed in the form of embedded submanifolds. Here we were able to show that with just a few simple modifications, we could extend what we did with Euclidean spaces to work for curved surfaces as well. Videos 76 to 87 were devoted to the subject of curvature. The main takeaway here is that curvature can be analyzed from two very different perspectives. The extrinsic, or bird's eye view, is based on our knowledge of how the submanifold is embedded within the ambient space. The intrinsic, or bug's eye view, relies entirely on measurements that can be taken within the confines of the submanifold itself, and is completely independent of how it's embedded. In videos 88 to 99, we turned our attention to the subject of curves. This led to a couple of very important new concepts, including geodesic curves and the parallel transport. Now, there are a number of additional topics that you may want to research on your own. These include geodesic deviation, surface trajectories, Gauss's theorem, Stokes' theorem, and moving surfaces. I chose to skip these particular topics because they're just a little bit beyond the introductory level. Instead, I want to conclude the series with a very brief introduction to the topic of Riemannian geometry. Riemannian geometry applies to what we call a Riemannian manifold, which I will describe in more detail shortly. The manifold may be flat or curved and may consist of any number of dimensions. The resulting relationships will work for 20 dimensions the same way they work for 2 or 3. Most significantly is that there is no reference or dependence whatsoever on an ambient space. Everything depends entirely on intrinsic properties. There may or may not even be an ambient space. We simply don't care. What we're going to see is not necessarily any new relationships, but a totally new perspective from which those relationships are derived. As such, this should be a good way to end the series because it will solidify almost everything we've done into a single generalized model. Well, as you might suspect, there's no way to cover a topic like this in a single video. So the best I can do is to touch on the high points. This should at least give you an idea of how it works. So let's get started. Recall what we discovered in video 92. This relationship tells us how a surface is embedded in the ambient space. This one tells us how a curve is embedded in that same ambient space. What we discovered is that we can combine these two expressions along with this chain relationship to derive this expression, which tells us how the curve is embedded in the surface. Now, there are two very important takeaways here. First, since we did not reference a position vector, this final result is valid for curved surfaces as well as those that are flat. Second, the relationship is void of any reference to the ambient space itself. All of these z objects up here have been eliminated as part of the derivation. Thus, the relationship depends only on the intrinsic relationship between the curve and the surface. Now, this result, and others like it, led Gauss and his contemporaries to question whether we really need to reference the ambient space in the first place. Indeed, he was able to show that curved surfaces can be analyzed directly from the intrinsic nature of the surface itself, primarily its metric tensor. Riemann followed up shortly thereafter to show that this same analysis is valid in general for curved manifolds of any dimension. The results are what we now refer to as Riemannian geometry. Let's see if we can get an idea of how this plays out. We start by choosing u and u prime as alternate coordinates that may represent any number of dimensions in a space that may be flat or curved. They must vary smoothly and must be differentiable throughout the space. We forego the use of z, s, and u as coordinates since we don't need to reference embedded submanifolds. Next, we need coordinate transformations. Here we can derive the u values as functions of u prime, and here we can derive the u prime coordinates as functions of u. Next, we define Jacobian factors in the usual way. There's nothing new here. Now we define a contravariant vector as any set of scalar values that transforms as a contravariant transformation. In a similar fashion, we define a covariant vector as any set of scalar values that transforms as a covariant transformation. Notice we don't make reference to basis vectors in any way. Note here that dui is equal to the partial of ui with respect to ui prime times dui prime. And that means that du itself is a contravariant vector because this pattern is the same as this. And that's why we use an upper index for our coordinate variable itself. Now consider this expression involving a contraction between arbitrary contravariant and covariant vectors. Here we can perform a very simple proof which by now should be very clear and obvious. First of all, we can replace our two factors with their equivalents. These two factors can be replaced here and here based on these two relationships. Next, the Jacobian factors combine together to produce a Kronecker delta factor right here. And now the Kronecker delta will absorb the J prime index here to give us this final result. This sort of thing should be second nature by now. Well, because this expression in the unprimed system is exactly the same form as that of the primed system, that tells us that our value p here is an invariant scalar value. Next, we consider this form involving a multi-indexed factor right here times all of these non-zero arbitrary vectors to form a scalar value of p over here. We say that T is a tensor, in this case of rank 5, if and only if it equates to the identical form in the prime coordinate system. So if this form in the unprimed system matches this form in the prime system, then we can say that T is a tensor. This leads in turn to the equivalent expression for the general transformation rule for tensors. Now, all of this should be very familiar. It's exactly what we did in video 19. With all this in place, we can now work through all the syntax rules for tensor algebra that we explored in the early part of the series. There's really nothing new in all of this except for the new definition of vectors right up here. and the fact that we've not restricted the results to flat space, nor have we limited the number of dimensions. Well, let's move on now and talk about a Riemannian manifold. A Riemannian manifold is a space characterized by two properties. The first is that the metric of the space can be represented in the quadratic form that you see here. Now, the term quadratic derives from the fact that there are a pair of infinitesimal factors here and here. Gij itself is a scalar function, being a function of the coordinate u. In every case up to now, this metric equation is something that we've derived. However, for Riemannian geometry, we start with the metric equation as a given. After all, the metric tensor is an object that can be mapped out using intrinsic measurements. It is not dependent in any way on extrinsic curvature information. You might want to revisit video 81 for a refresher on this concept. Our first observation here is that this is a tensor equation. Well, how do we know that? First of all, ds here is the infinitesimal Euclidean length along a curve in our space. It's an invariant value that does not depend on the choice of coordinates. In other words, it is a tensor of rank 0. We showed just a few minutes ago that dui itself is a vector. Therefore, by the quotient theorem, gij is a tensor. This tells us that the relationship has the same form in all coordinate systems. So it would look like this in the prime system. Now, in every case so far, the metric tensor has proven to be symmetric. Is that the case here? Well, consider this. Any second-rank tensor can be decomposed into the sum of two tensors, one being symmetric and the other antisymmetric. In this example, Bij is symmetric, and Cij is antisymmetric. Since their sum is equal to Aij, then this relationship is true. Now we can easily see by expanding it out that this last term is equal to 0, which means that this term is equal to this one. Therefore, if Gij is not symmetric, we can always replace it with an equivalent tensor that is. Thus, we can always treat Gij as a symmetric tensor with no loss of generality. One of the most important properties of a space with this type metric is that at any point it's possible to derive and transform to what we call geodesic coordinates. Geodesic coordinates are those for which the metric tensor consists of plus or minus ones down the diagonal with zeros everywhere else. This should remind you of Riemann normal coordinates, which we introduced in video 83. What we have here is the same thing, except for the fact that the diagonal elements may be either positive or negative. What this leads to is a metric equation that looks like this. The pattern of plus or minus ones constitutes what we call the signature. Now, it turns out that transforming to geodesic coordinates at any point in a given space always yields the same signature. The geodesic coordinate system will be different from point to point, of course, but the signature is the same. In other words, the signature is a property of the space itself, not of the coordinate system. Well, this concept gives us a way to formally define Euclidean space. Euclidean space consists of a constant metric tensor and a signature of all positive ones, as illustrated here. This brings us to the second property of a Riemannian manifold. A Riemannian manifold is one that is characterized by a quadratic metric and has a signature of all positive ones. This means that at any point within the Riemannian manifold, we can transform to a locally flat Cartesian coordinate system. Euclidean space is itself just a special case of a Riemannian manifold. When the signature does contain one or more negative ones, the space is classified as pseudo-Euclidean, and the corresponding manifold is called pseudo-Riemannian. What you see here is a real-life example from general relativity. Einstein was able to show that the quantity ds here, known as the space-time interval, is an invariant scalar quantity within a four-dimensional pseudo-Riemannian manifold with this signature. The good news is that all our analysis applies to both types of manifolds pretty much the same way. Okay, let's move on. Let's say that we find a vector ti prime that is constant throughout the manifold. Its derivative with respect to a parameter lambda, of course, will be 0. Well, now transform to the unprimed system. This is just a contravariant transformation, and because of this derivative factor, it's clear that even though ti prime is constant, ti itself is not necessarily so. Therefore, when we take the derivative of this expression with respect to lambda, we get this. This part of the expression is just the chain rule applied to this first factor, and of course ti prime itself is constant. But what we really would like to know is how this relates to the corresponding factors in the unprimed system. So to see that, we need to apply the chain rule to each of these last two factors. This term right here is the equivalent of this one, and this term is the equivalent of this one. Now collect all the scalar factors together into a single function of u that we call affine connections, or just connections. Okay, a quick spoiler alert here. In most literature, you see this defined as a positive variable. But I've chosen negative gamma deliberately here because I know where this is headed. Further analysis will show that connections are just the negative of the Christoffel symbols that we're used to. So defining them this way is less confusing. Just for kicks, you might want to see if you can derive the Christoffel symbols for plane polar coordinates from this expression. Just choose r and theta for u, and x and y for u prime, and plug into the formula. This will prove to be instructive, but as you'll see, it's a pretty cumbersome process and not very practical. What's really important here is the form of the vector derivative that results. So using this definition, we can express this relationship this way. Note this is a bilinear expression. The derivative here is proportional to both the coordinate displacement and the vector itself. The connection is a scalar value of proportionality. Now, all the factors in this expression are functions of u, which makes this an intrinsic relationship. There's no dependency whatsoever on u prime. Now, of course, we derived this for the special case where ti prime is constant, but it can be shown that the form of the result is valid in all cases. We can also express the result in differential form, which you should immediately recognize as one of the forms of the parallel transport that we derived in video 96. One final point here. Note that this form is also valid for a constant vector. For example, the derivative of ti prime can be expressed this way, provided the connections are all equal to 0, of course. Now, it turns out that it's impossible to transform the connections to a system where all the connections are 0 unless they are symmetric in the lower indexes. So the fact that we can transform to geodesic coordinates at any point in the manifold means that the connections are symmetric in the lower indexes. This is a property that's not true in all types of spaces, but it is true for Riemannian manifolds. Okay, all we need now is to find a practical way to evaluate the connections, and for that, we appeal to the metric compatibility property discussed in video 96. The metric compatibility property says that when we parallel transport two vectors together, their dot product will remain constant. Well, this is one of the forms for the dot product between vectors t and q. We'll also stipulate here that they are both non-zero. Now, since this dot product is constant during the transport, its derivative with respect to the curve parameter lambda has got to be equal to 0. Well, expand this out using the product rule. Note that this combination of factors right here is really the chain rule applied to our metric tensor right there. Now replace these factors, this one and this one, with the equivalent expressions for the parallel transport. This factor right here is the same as this, and this factor is the same as this. Now we can rearrange the expression, and after some simple index swapping and renaming, we get this. Remember that both the metric tensor and the Christoffel symbol are symmetric in the lower indexes. Well, next we can divide out all of the common factors, and that would be these factors right here. They're in each of the terms and will divide out across the board. Now, note that the metric tensor here and here will lower this upper index right here. That yields this expression, which is the same one we derived back in video 30 using a different method. From here, we can derive the explicit formulas for the Christoffel symbols in exactly the same way we did in that video. Thus, we have derived expressions for the Christoffel symbols using only intrinsic relationships. Okay, we're almost done here, but I want to show you one more thing. Suppose we have some vector field Ti. Here it points in this direction, and over here, a small distance du away, it points in this direction. Well, for a vector function like this, we can relate these two values using the first two terms of a Taylor series expansion. Remember, because we're dealing with infinitesimals, we can ignore all but the first order terms. Well, now let's parallel transport vector Ti along the same path to produce vector Ti star. Note that Ti and Ti star are not the same thing. Ti here is the actual value of the vector field at this point. On the other hand, we get Ti star by parallel transporting vector Ti all along here. We're transporting it parallel to itself until we reach this point. Okay, we'll expand this out using our expression for the parallel transport. And now we're going to consider the difference between these two results. We're going to take this result and subtract this one. Okay, well now we can simplify this expression, and what we get looks like this. And you should recognize this immediately as the covariant derivative. This gives us a new intrinsic perspective for the covariant derivative. It is the difference between a vector and its corresponding parallel transport. This part of the expression is the term that represents the actual vector change, while this part of the expression is due to the coordinate system effects along the same path. Note that this is a tensor. This is a vector difference, which means this is a vector, and of course we know this is a vector, and because of the quotient theorem we know then that this factor is a tensor as well. All right, well that's all I'm going to say about Riemannian geometry. I blew through all this pretty fast, and I'm sure you have more questions than answers. But at least hopefully you now have some sense of how one goes about deriving intrinsic relationships without reference to extrinsic curvature information. It would clearly take many more videos to fill in all the steps in a rigorous fashion, and we simply don't have time for that. So we'll have to end the video here. It's also time to bring the entire series to a close. My goal has been to give you an introductory working knowledge of tensor calculus, and I believe I've done that to the best of my ability. So I bid you farewell at this point and wish you well as you continue your mathematical pursuits, whatever they may be. So goodbye for now, and thanks for watching.